EES, which is pronounced EASE, is an acronym for Engineering Equation Solver. EASE is an engineering tool, and therefore the variables in EASE typically represent physical quantities, often measured quantities. In the previous videos in this section, we saw that EASE variables that represent measured quantities can be assigned uncertainty, and then this uncertainty can be propagated in order to determine the uncertainty in other calculated variables. In this video, we'll see how best to use this capability in order to process a table of data. So let's consider the example that we looked at in the previous video, where the heat transfer coefficient associated with internal flow through a duct is being measured. For this experiment, the measured variables are summarized here along with their uncertainty. And we had set up an EASE program to analyze just one data point corresponding to the measurement values that are shown here. These measurements are then used to determine the heat transfer coefficient, as well as the Reynolds number, the average Nusselt number, and the friction factor, along with their uncertainty. So let's examine the situation where we have a set of data corresponding to a series of tests. So these data are contained in an Excel file as shown here. And you'll notice that the cross-sectional area, perimeter, and length of the duct, those measurements are assumed to remain the same. These measurements then just include the flow rate, the temperatures, the pressure, and the pressure drop for each data point or each test. The first and the second rows provide the names and the units of the measurements respectively, and then the remaining rows contain 4 sets, in this case, of measurements. Looking back at EASE, we have already set up the uncertainty calculations as we want to in our previous example. So this is doing the uncertainty calculations and the calculations for a single data point. And if we select uncertainty propagation, we can look at the measured and the calculated variables that we've selected. And if we select set uncertainties, we can see all of the uncertainty values that are set for each of the measured variables. This information can be saved using the Save button down here, which saves the uncertainty information to an uncertainty information file, a .unc file that contains this information, and then can be reloaded in the event that we want to reset to these values. So here we're going to load the data from the data file. So if we select Open Lookup Table from the Tables menu, and then we change the file extension to .xls, we can see our data table, and you can see the data are now contained in this lookup table, which we call data. We can use the lookup command to read data from each row of the table. So the variable row is going to contain the row of data to be read. So here, if I'm going to solve from the equations window, I'll just set row to 1, and we'll look at only the first data point. But if I'm going to run with a parametric table that looks through all of the rows of the lookup table, then I'll want to set row to table run hashtag, which is a constant that returns the current row number of whatever table I'm running. So switching between these two modes is accomplished using the $if directive as shown here. I'm going to set the string table $ to contain the name of the table to get the data from, and that lets me then easily switch from one set of data to another. And you can see then here I'm reading the data and I'm converting them all to base SI units as they are being read. So now we can set up a parametric table that contains all the variables that are of interest to this analysis. So here we're going to include all of the measured variables as well as the calculated variables. And then there's 4 rows in this parametric table that are going to correspond to the 4 sets of data in the lookup table. So if I want to run through these calculations, including the uncertainty propagation, I need to select Uncertainty Propagation Table. And then if necessary, I can load the uncertainty information file, the .unc file that I saved. And then if I hit solve, you can see that both the values and the uncertainty of each variable are recorded. So if I want to make a plot now, the uncertainty that is associated with each of these values can be used to automatically make error bars. So for example, here I'm going to plot the Nusselt number versus the Reynolds number, and you can see that the error bars are set based on the uncertainty of the table. I can do the same kind of thing for friction factor versus Reynolds number with the error bars set. So you'll note that the uncertainty values are not saved when you save your EASE file. So if I save this file and I reopen it, all the uncertainty information in the parametric table is gone. And what that means is if my plots are set to auto update, this loss of uncertainty information will also correspond to a loss of all of my error bars in these plots. And in order to restore the uncertainty information and the error bars, I would need to redo the uncertainty propagation table command in order to repopulate this table and restore my plots. And that's fine, but I can avoid this by saving the uncertainty values of interest separately, and I would do that by accessing those uncertainty values using the uncertainty of command that we talked about in the previous video. So here I'm going to access the uncertainty of the calculated variables using the uncertainty of command in the equations window, and then I will add columns to the parametric table to store these uncertainty values separately. Now the uncertainty values are going to be saved when I save my ease file. Furthermore, I can use the uncertainty values in these columns to make my error bars, and they will persist even if auto update is selected. So here I'm going to make a plot of Nusselt number versus Reynolds number, and once the plot is made, I'm going to link the error bars up to these columns in the table as shown here. So now if I save my file and reopen it, you can see that that information is all retained and the error bars persist even if the auto update is selected for this plot. In our next video, we'll look at how to use the uncertainty propagation feature in ease to help design an experiment rather than to analyze data after the experiment has already been run. This is one of a series of tutorials that is meant to describe the operation of the ease software. If you'd like to get more information about ease, obtain the software, or access more of these tutorials, please go to the website fchartsoftware.com. These tutorials are excerpted from the book Mastering Ease, which can also be obtained from this website.